Okay, let's take a look at some announcements. We did the floating stability experiment on Tuesday morning, and the report for that will be Tuesday the 7th. And then we're going to do a flow visualization experiment that day. Hard to believe we're already going to be on Lab 7. This semester is really flying by. We'll flip the lab groups again, have Group A at 2 o'clock, Group B at 3, and then the next assignment's due a week from today, homework set 4A. The exams, I've started grading them. I'm about 2/3 of the way through the exams. Normally I like to turn it around so that I'd give it to you the very next class period, but I was busy working on some graduate stuff yesterday, and I really like to give as much partial credit as I can, and to do that I have to understand your solution. I'm having trouble understanding some of the solutions. I know when you're pressed for time, it's easy to, here's a piece of paper. When you're in a rush, I do the same thing. I'll start working here, then I'll go down here for a bit, then I'll go there, then I'll go here, and so in some cases I'm trying to, it's like CSI. All right, I start here, then I go down there. I'm trying to piece together the evidence so I can give you as much partial credit as possible. So, long story short, I'll have the exams to you on Tuesday, but I'll probably post the grades today or tomorrow. If you want to beat yourself up and look at the exam grade over the weekend, let it ruin your weekend. Log on, go nuts. Yeah, just get it over with. I made the mistake one time, my first semester teaching college, I looked at the student evaluations on Christmas Eve. Big mistake. Because it was my first semester teaching, and this was a vicious group of students. It literally, I was in a funk for about 3 days. It ruined, yeah. It was my youngest son's second Christmas, so I just sat there feeling gloomy. The joy in his eyes meant nothing to me because all the daggers in my back. But it doesn't bother me as much anymore, and I don't look at them on Christmas Eve either. So we're talking about Chapter 4 stuff, and this is big news because previously we've only been doing fluid properties and hydrostatics. Finally, we get to start talking about the fluids moving. And so why does fluid motion matter? Why are we excited to start thinking about particles moving and the fluid? Yeah, it's the real deal of civil engineering. In civil engineering, sometimes we have static fluids, and so you can the water on the left side of this dam can be approximated as static, but what happens inside the dam, the forces of the fluid as they move through a turbine, the amount of energy that's exerted on the bottom of the stream channel as those jets of water impact the channel. Fluid motion is the majority of the water out there is moving somewhere, whether it's in the subsurface or over the surface. So there are two different approaches for trying to break fluid motion up into pieces and try and understand what's the velocity of the fluid, trying to track where it's going over time. And the Lagrangian approach answers the question of what is the fluid velocity by using a frame of reference that tracks individual particles. And so it has a certain field of analysis. We're looking at the particles that are in this box. And the Lagrangian approach says, let's look at each individual particle. Put your head down on your desk. It looks at each particle, and it tracks that individual particle over time. And so the path that's traced by each particle is called a path line. And we're also going to talk about other things that are streak lines and streamlines today, and we'll have an activity for drawing path lines. But the Lagrangian approach has a limitation, and that is it's really hard to keep track of all the particles in a flow field because there's going to be a lot of them. If you're going to do it at the molecular level, it's hard to track every particle. And so instead of following every particle, what you'll sometimes do when employing the Lagrangian approach is you'd use this particle to represent the particles that are around it. So this one is going to sort of be like the approximation. It's a little bit like a poll ahead of an election. One person approximates the behavior of lots of others. And so this one particle is used to approximate those in the surrounding areas. So in the Lagrangian approach, the coordinates, the location of each particle is tracked over time. And so in this approach, the velocity of a particle over time is going to be broken up into its x, y, and z components. And so when we're talking in 3 dimensions, we don't have to just think about the vertical and the horizontal, but now also there's a 3rd dimension into the page. And so we can have an I, j, and k, and each of those are 3-dimensional coordinates where we have a velocity in the x, y, and z. So u, v, and w, we're just talking about the magnitude of the velocity along a certain axis over time. So there's the Lagrangian approach, and the other approach to determining how is the fluid moving is the Eulerian approach. And instead of tracking individual particles, the Eulerian approach says, let's break our field of area, this big box, into smaller pieces. And then what we'll do with this mesh of pieces is we will say that the velocity inside of this window is a certain direction. And so we'll assign every particle inside of this window a certain velocity at a certain time. And so it's not tracking a particle that's moving over time, because in this first approach, inside of our window, the particle is moving in the window. In the Eulerian approach, our window is stationary, but what we're doing over time is we're assigning behavior to the stationary window. And so we're going to be saying, what is the velocity in 3 dimensions? What's the x, y, and z velocity of this at a certain time? So at time t, each window has a velocity in 3 dimensions. And so we'll look at different ways of applying both of these methods. But the important thing is to note that you can't track every particle, and so there have to be simplifications in order to approximate the behavior of the entire flow field. All right, here's another car. We looked at a car when we were talking about pressure, because the pressure of the tires. But this picture is going to give us some information about what's happening. So what can we learn related to fluid mechanics from this picture? Okay. So the velocity is greater at the top than at the bottom. So you're talking about up here? All right. How do you know that the velocity is bigger here than it is down here? Okay. All right. Well, one thing we can tell from the picture is that it's windy. You know, that this car is in a wind tunnel. I mean, maybe that's so obvious we didn't even think to say it, but the fact that there's these little lines of smoke going over it tells us that it's in some sort of a wind tunnel. And we can also tell what direction the wind is going. Is the wind going this way, or is it going that way? The first way. How do we know it's going this way? We can tell from the picture, but how do you know? It's breaking up at the tail end. That's called diffusion. And so there's probably some sort of like a pipe up here that has nozzles, and the nozzles are injecting a smoke, and as the smoke spreads out, it's getting broken up at the end over there. And so without even thinking about it, we can look at this picture and tell there is velocity. We know the direction of the velocity. It also gives us an idea of the relative magnitude of the velocity. And this is what Taylor was getting at, is that the velocity isn't the same everywhere on this car. The velocity is faster here than it is down here. And this is a bit of a isometric view. So our brains correct for that automatically. But even though it's an isometric view, you can still tell that these lines are closer together up here. You know, it's far apart here, and it's close together there. These streamlines, when they get closer together, that means that the fluid velocity is accelerating. And so, you know, why is it accelerating? Well, this is actually Bernoulli's effect. And you maybe have heard about Bernoulli's effect if you went to a children's museum. They always have some sort of a display. Have you ever seen the typical children's museum thing where there's wind going up and then what's suspended in the wind? It's like a little ball, right? And it's sitting there floating in the wind. And so that's a manifestation of the Bernoulli effect, is that it's generating lift as it goes around that ball. As the wind goes around the ball, it holds it stationary. Another time that we talk about the Bernoulli effect is when we are designing wings and air is going over the top of the wing faster than it goes under the bottom of the wing, and that's what generates lift. We'll talk about the Bernoulli effect in detail, but part of the reason why they have the spoiler on the back of this car is, number one, because it looks cool, and we can all agree with that, right? That's why we put spoilers on the back of our Chevy Cavalier. It's because it looks cool. But then the other reason why we put the spoiler on the back of our Chevy Cavalier is to ensure that there is a downward thrust on those back wheels, so we get maximum traction, because the car actually is generating lift. If you look at the shape of that car, it's a little bit like the shape of the wing. Flat on the bottom, curved on top. So that car is going to be generating lift unless we have that spoiler on the back trying to spoil the lift that's being generated and push the back tire down a little bit so that it's able to get traction again. So, so the main thing, besides there is fluid movement, fluid being an air here, you know, gases are fluids, liquids are fluids. Those are the two categories of fluids. So there's fluid movement, we know the direction, and we know that there's a faster velocity on the top than in the front. So visualizing flow. We're going to be talking about flow visualization today and different types of flow. That's the main part of today's lecture, is types and visualizing it. So streamlines are what we just took a look at, the light blue velocity vector that we see here. This is two different kinds of flow. This is open channel flow on the left and closed conduit flow on the right. So open channel flow, we can tell that it's touching the air above it. In this case, because of these little hash marks, that's indicating ripples. Sometimes I put the triangle above it, but this is a sloped channel, and the velocity is indicated by those blue lines. It tells us the direction of the flow. And just by looking at these streamlines, I don't know whether it's 1 foot per second or 10 feet per second. The magnitude of the velocity isn't indicated on an absolute basis. Now on the right, this is closed conduit flow. What we're looking at is the cross-section of a pipe. There's a pipe wall on top, a pipe wall on the bottom, and it's a circular pipe, so it's going all the way around. Again, we can draw streamlines that's indicating that the flow is going, with these little arrowheads that are on here, the flow is going from left towards the right. Visualizing flow, we can again draw streamlines if we have a tank and put a hole in the side of the tank, an orifice. And you can notice that in this case, now those lines aren't parallel to each other like they were initially in this channel that was doing uniform flow, and this pipe had uniform flow. So now I'm throwing a term out there, uniform flow. Uniform flow is when the streamlines are parallel. You know, it's nice and uniform. Now this is not uniform, so we call it non-uniform flow. You notice that the streamlines aren't parallel to each other. That means that some aspect of the velocity is changing. And in the case of water flowing out of a tank with a hole in the side of it, there's a change in the fluid velocity in terms of its magnitude and its direction. You know, the water is moving downward and then it starts moving sideways, and so that's the direction of its velocity. And then the magnitude is the fluid is accelerating. As it gets closer to that opening, it's moving faster towards the opening. So non-uniform flow, non-parallel streamlines. Here is showing a wind going under and over a wing, and on the front end of that wing is a stagnation point. And a stagnation point is when a streamline just basically stops at a dead end. And what a stagnation point results in is a localized increase in pressure. And again, that goes back to Bernoulli's equation, which we'll talk about in a future lecture. It's in chapter 4. So it won't be too long until we're talking about Bernoulli's equation. Here's more examples of non-uniform flow. Here's a pipe where the diameter is getting smaller. If the pipe diameter is getting smaller, then the fluid velocity has to increase in order to achieve the same flow rate in and the same flow rate out. So here, since these lines are getting closer together, that means that the velocity on the opening side, on the inlet, is lower than the velocity on the outlet. And then on the far right figure here, it's showing rotational flow. Again, it's non-uniform because the direction of the velocity keeps changing. Even if the magnitude or the speed is the same, as the water flows around in a circle like a vortex, whether it's a hurricane or like a sinkhole that's draining water, if it swirls around in circles, the direction of the velocity changes, and so that is the definition of non-uniform flow. So here we're talking about non-uniform and uniform flow. The definition of uniform flow is when the velocity is constant in the direction of the streamline. That means with respect to position, the velocity isn't changing. The velocity is the same on the left side of the flow field as it is on the right side of the flow field. As the flow moves in the direction of flow, it's not speeding up, slowing down, or changing direction. Everything's uniform in an open channel and a closed channel. The change in velocity with respect to position, here S is referring to position. So the change in velocity with respect to changing position is 0. There's no change in velocity as the position varies. Now, non-uniform flow is when the velocity is changing. And here are those diagrams that's showing non-uniform flow. Here the velocity is increasing as we go in the direction of flow. So dV ds is not 0. In fact, it's, in this case, going up. Here it is just the direction component of the velocity that varies rather than the magnitude. So the first of many different ways we classify flow, we're going to break flow up into, is it steady or is it unsteady? So it's velocity as a function of position. The next way that we're going to divide flow up when we try and classify it is into how the flow changes over time. Not necessarily position. Uniform, non-uniform is all about position. Steady, unsteady is about how flow conditions change over time. It is, I see flow right now. What is the flow going to be like in 5 minutes? Is it going to be the same as it is now for the location that I'm looking? Or is the flow in 5 minutes going to be different? And if it's constant over time, if there's no change over time, we call that steady flow. And if it is varying over time, we call it unsteady flow. Now, I don't have any pictures shown on the screen right now. I had pictures to show you when it was uniform versus non-uniform. How come I can't show you a picture, a single image, that differentiates between steady and unsteady? Because a picture is just at a single instant in time, and the whole essence of steady versus unsteady flow is over a period what's happening. So from one time to the next. And so a single image doesn't give us any information about whether flow is steady or unsteady. And so we have to use a video or a sequence of images in order to illustrate the difference between steady and unsteady flow. And I've got a video to show you that illustrates what unsteady flow looks like.
Just right here to the left.
This is in Arizona.
High ground!
And they hear something.
I'm going to film it. Oh, there it is. Here it comes. Here it comes. Wild. Whoa, it's coming quick.
Yeah, it's big one.
Awesome.
Big one!
Should I probably get out of the way?
Starting to get a little anxious.
Oh,
Let's
yeah,
step
I
aside.
Dang, it's bigger than the last.
That's not chocolate. It looks like chocolate, but this is not. It's moving. The water's moving so fast.
Wow, it's bigger than the last.
Really excellent illustration of
we know what to look for. That's crazy. It hasn't even been raining.
Time are not equal to the conditions at
That is so deep.
It's also a good illustration.
Yeah.
It seems like it's not raining there. It's raining somewhere. It's not raining
I hope
there.
those people have enough sense to get out of the way.
433 civil engineering, 433 capacity teaching. After hydraulic engineering, we talk all about how do you predict events like that. So that's an illustration of unsteady flow. So flow can be uniform versus non-uniform, steady versus unsteady. Those are talking about two separate different things. Flow as a function of position and flow as a function of time. Other ways to classify flow is by laminar versus turbulent. And laminar flow is a very smooth, slow-moving water, and the way that we calculate the Reynolds number, which classifies whether flow is laminar, if the Reynolds number is less than 2,000, then we know the flow is laminar. That is a function of the density of the fluid, the velocity at which it moves. If it's inside of an enclosed pipe, then we would account for the diameter of the pipe, and then finally all of that is divided by the viscosity of the fluid. Reynolds number is a unitless property, so that all of these three things in the numerator multiplied together will have the same units of newtons seconds per meter squared that viscosity has. And so when we divide the numerator and the denominator, there's no units remaining. So laminar flow is very smooth, and it's characteristic of very little energy is going to be lost when conditions are laminar. And the flow doesn't spread out as much. Remember the diffusion that we saw in the first image of the smoke going over the top of the car? Those smoke streamlines will spread out less in laminar flow than they will in turbulent flow. Next Tuesday, we're actually going to have a chance to visually see laminar versus turbulent flow in the lab. Now, turbulent flow is when this property called the Reynolds number is greater than 4,000. And it's typical for water moving at a high velocity through a pipe network, or if it is a ship wake or the wind that comes behind a truck on the road. It's like lots of turbulence, and so a Reynolds number of greater than 4,000, but then there's this transition range in between, where between 2,000 and 4,000 we don't know exactly whether it will be laminar and turbulent. It could be one or the other depending on what direction you're coming from. And by that I mean if you had a pipe and the water is moving through it very slowly. If conditions are laminar to begin with, and you're gradually increasing the flow velocity just a little bit, then in this uncertain intermediate range between 2,000 and 4,000, it will stay laminar for a long time until there's some disturbance that will then force it into the turbulent regime. So if you bang on the pipe with a hammer, then suddenly it might transition into turbulent flow. Likewise, if the water velocity is very high moving through the pipe and you're gradually decreasing the velocity so that the Reynolds number is going down and down and down, it will stay turbulent until it reaches about 2,000, and then it switches into the laminar range. So we have an example here. I'd like you to get a crack at this unitless property of Reynolds number. We have a pipe that's 2.5 meters in diameter, and the velocity that's moving through the pipe is 0.1 meters per second. What is the Reynolds number under those circumstances? And then part B is asking what's the maximum flow velocity that you can have, and still the Reynolds number will be equal to 2,000. Or in other words, that you can guarantee the flow that will be laminar. In the problem statement, I haven't given you the viscosity of the fluid. And a typical viscosity of the fluid is 1 times 10 to the minus third Newton seconds per meter squared. That's a typical, if you don't know what temperature the water's at, you can use this parameter for the viscosity. Let me show you one other simplification. Did I say to the third? No, it's to the sixth. Let me just make sure here. Sixth. No, okay. It's the kinematic viscosity that is 1 times 10 to the minus sixth meters squared per second. And the reason why I also provide kinematic viscosity is that the Reynolds number, which is density, velocity, diameter divided by viscosity, can be approximated or simplified to velocity, diameter divided by kinematic viscosity. And the reason for that is that, remember, kinematic viscosity is viscosity divided by density. And so over here, if we've got 1 times 10 to the minus 3 Newton seconds per meter squared, and divide that by 1,000 kilograms per cubic meter, then we end up with 1 times 10 to the minus sixth meters squared per second. So I'll pause for a moment and let you take a crack at part A and part B here. What's the Reynolds number for the velocity that's specified, and what's the upper limit velocity that we could have through this pipe and still observe laminar flow? It'll be laminar. Yeah, I should change that to Reynolds number is less than or equal to 2,000. But they call it transition. The flow will be laminar or turbulent, but the zone between 2,000 and 3,000 is 2,000 and 4,000 is indeterminate. It depends on the flow conditions prior to what you're seeing. How did it get to 3,000? Did it get there because it was fast and now it's slow, or did it get there because it was really slow and now it's relatively slow? So I did it as the velocity times the diameter divided by the kinematic viscosity. So it was 0.1 meters per second, 2.5 meters, the diameter of the pipe, and then 1 times 10 to the minus sixth meters squared per second. So even though it's moving really slow, 0.1 meters per second is pretty slow moving water, it's still considered turbulent flow. So when we're in the lab next Tuesday, we're going to be looking at water flowing through a little pipe, a tube. And we're going to inject a dye into the center of that pipe so that we can watch the die and see if it gets scrambled or if it stays in a straight line. And it's going to have to be moving super slow to not get scrambled up, because here 0.1 meter per second is hardly moving at all, and it's still turbulent. And so part B of the question asks, how fast could the water be moving and still experience laminar conditions? And so if we let Reynolds number equal 2,000, then the velocity is going to be the Reynolds number times the kinematic viscosity divided by the diameter. If we rearrange that equation for the Reynolds number, so our maximum permissible value for the Reynolds number of 2,000 multiplied by 1 times 10 to the minus 6 meters squared per second divided by 2.5 meters, that means that the velocity has to be 0.0008 meters per second. In other words, it will be moving 0.8 millimeters per second. That's pretty slow. And in fact, the water will be moving really slowly through the little tube that we're using. Although in the lab, the diameter is going to be smaller than this 2.5, and so that will change the velocity of the water flowing through a tube. Any questions on how to compute Reynolds number? Just another way to classify the flow. So what we've talked about so far is uniform versus non-uniform, steady versus unsteady, and laminar versus turbulent. So we're breaking the flow up into lots of different flow types to be able to describe what's happening to it and how that affects the forces that we see and the behavior of the fluid. Here is a comparison. There's uniform versus non-uniform, steady versus unsteady. So what is it talking about? When we're trying to classify whether flow is uniform or non-uniform, the key thing here is position. Change in velocity with respect to position. Whereas in the classification of steady versus unsteady, it's change in velocity with respect to time. Now this slide that I'm showing you right now is pretty empty. Later on, through the rest of Chapter 4, I'm going to fill up this slide because we're going to have certain equations that deal with uniform flow versus non-uniform flow, some kind of equations that deal with steady versus unsteady, and we'll be able to actually break up all of these coming concepts into the main questions that they resolve is how does the velocity or the pressure change because of some force that's being applied to the fluid. And so this is the reason why there's so much dead white space down here, is that you'll see this same slide but with more information in future lectures as we sort of flush out all these concepts that are related. So that first picture that we saw of the fancy car in the wind tunnel, that was an illustration of flow visualization, and streamlines are a way of observing not the absolute magnitude of the velocity but of observing the relative velocity, and it tells us the direction of the velocity vector but not the magnitude. A path line, remember when we were looking at the Lagrangian approach to identifying the velocity, the Lagrangian approach was look at a single particle and follow where does it go. And that's what a path line is it shows the movement of a particle over time. A streak line is similar but a little bit more complicated. And what a streak line is if you started injecting dye into a fluid or some sort of a tracer, and then the fluid is moving around, then the location of that tracer or dye tells you the history of where the flow was. And let me illustrate that with just a little drawing I'm going to put on the board here of there's a river, and let's just for sake of argument say it's the Ohio River, and then there's the bridge that goes over the river. Okay, so here's the river and then here's the bridge. The water's moving this way. Okay. If I'm walking across the bridge and I throw in a well, let's not make it too gruesome. If I throw in a can, I was going to throw in a body, but all right. So I throw in a can, then the can just floats down the river, and the path line, you know, if the water's just moving straight like this, then the path line, you know, here's the can right now, here's the can in 1 minute, here's the can in 2 minutes, here's the can in 3 minutes. If I connect the dots, then the path line shows us what's happening to the fluid movement, because that can that's floating in the fluid is sort of an approximation for what the fluid that it's surrounding is doing. It's the behavior of it. So I threw in a can. I'm a litter bug. Now I'm going to take it to the next level. I'm going to start pouring paint in the river. All right? So I'm walking across the river. I'm on this side of the bridge. I got a big bucket of paint, and as I'm walking, I can hardly carry it. I'm walking across the river, and I'm pouring paint in. I start here, so I start pouring, and then I'm walking across. What is it going to look like in the river? It's not going to be straight like the path line was. It's going to be at a streak, right? There's going to be a bit of an angle, and it's going to be like when I make it to this side, when I'm finally over here, here's start, and here's finish, and I'm still pouring in the paint over here. It's going to look like this. You know, here's the first little bit of paint that I poured in. It's been sort of washed downstream. And then here's the paint that I'm pouring in right now. And so that is a streak line. It's showing like the streak of not only the movement of the fluid, but it's also showing my movement, because the fluid is just moving to the side. The reason why this is at an angle is because I was waddling across the bridge as I carried that big bucket of paint that I was pouring in. All right? So streamlines, path lines, streak lines, all three of these are used to help us visualize flow. So here's an illustration that's in the textbook that tries to show you streak lines, streamlines, and path lines. And before I show you this illustration from the book, I have to just lay the groundwork, because the picture, when you look at it, there's so much stuff drawn on top of itself that you can't really interpret it unless you spend a lot of time staring at it. So here's the scenario that's going to be illustrated in the following figure. Before some certain time that we're going to call T0, that's like the dividing point. There's before T0 and then there's after T0. It is the event that divides time. Before that, the flow was going to the right, and then after that, then the flow was going at an angle. So there's only two periods. There's before and after, and the flow is going two different directions during those periods. And so here's the illustration. Here it's showing these blue lines are the ones that are horizontal, that are pointing to the side, are the streamlines for before T0. So T is less than T0. That means it's the streamline before this dividing event. And then after T0, then the streamlines are going at the angle. Okay, so these two figures here are showing path lines. And so here is a tracer of some sort. It's a single object that's been dropped into the fluid. It's a can, whatever. It's floating, and it floated to the right, and then when the flow changed directions, now the can is traveling at that angle. And so path lines are easy to draw. But what's a little bit more tricky to draw is the streak lines. And sometimes we get tempted into thinking, well, streak lines are just the inverse of a path line or something like that. But that's not true at all. It's just coincidental in this figure that it looks like a mirror image of some sort. I'll give you a handout in a minute that disproves that idea. But what a streak line is, remember when I was walking across the river and pouring in the paint, in the streak line, we're pouring in our tracer at the same location through the entire two time periods. And this is the first drop of paint that we poured in. It's been pushed all the way over here. That's the Chevy with the big fin on the back. What was it, a Cavalier? That was a cavalier. I can hear, here's the paint from the beginning, and here is where I'm still pouring in the paint at the very end. So you can see the shape that it made by the changing direction of the flow. So here's an example. Let me hand it out now so you can get practice drawing these. Use pencil. Don't start with pen. Don't get too confident because these are tricky, especially the streak line. Now, I don't need to collect these. I know I collect a lot of the in-class exercises, but this one is just for you. It's not for me. But I still would encourage you to work with a partner on attempting this. So there's 3 different time periods in this one. Oh no, wait, this is a separate example. Okay, we'll do this handout in a minute. Let me show you the one that's on the screen here, and then you can go to the handout. All right, so the example that's on screen here is not the same as the handout example. Let me do the one that's on screen. There's 3 time periods, and it goes to the right for 9 seconds, down for 4, then to the left for 6. Okay, so our path line will look something like this. It will have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then down for 4 seconds, 1, 2, 3, 4, and then to the left for 6. 1, 2, 3, 4, 5, 6. So here's where it started, and here's the end. And that's our path line when we connect the dots. Pretty simple to do path lines. Now, the streak line, the way that you draw a streak line, the best tip I can give you is don't move your pencil, move the paper. Because the paper is sort of, the paper is the flow field, and if you're going to continually inject some tracer dye at the same location, then you want to move the paper as though it's the flow field. So I'm going to hold my pen in the same place, and then I'm going to move the paper in the direction that's specified by these arrows. So here I'm going to start off with flowing to the right for 9 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now the paper needs to go down. I backed myself into a corner here. 4 seconds. 1, 2, 3, 4. Okay. And then to the right for 6. 1, 2, 3, 4, 5, 6. So here is where, this is where it started, and here's the end. So that's what the streak line looks like. So now you do the same approach on this handout I've given you. We've got 4 time periods instead of just 3. The path line will be easy, but then the one wrinkle is just to make it a little bit simpler. What I've said is that the velocity increases when it's at an angle. So you see this time 5 through 9. When it's traveling at an angle, then the velocity suddenly becomes 1.41 times faster. And so what me telling you that, it means that it's always going to be one block. It's just to make it easier to always count 1 second is equal to 1 block. Right, right. So when it's going at an angle, the block path is longer than it would be if it's just one of the top or the side lengths. Okay, so I'll stop talking, let you collaborate, and do your best to draw the path line and the streak line for that example in the handout. We've been talking about velocity. And no discussion of velocity is complete without a discussion of acceleration. It's where velocity comes from, if you think about it. Fluid velocity from acceleration, there's different types of acceleration that we're going to be talking about this semester. The type of acceleration that most people think of when they are coming from a background of physics, they're thinking usually about something that we call local acceleration. But velocity can change as a function of time, or it can change as a function of position. And so you think about the particle that's moving along some curved path. And the two components of acceleration here are the acceleration that's tangential to its direction and normal to its current direction. The tangential acceleration is related to a change in speed, or the change in magnitude of its velocity. And if we have a change in its direction, then that's a centripetal acceleration that's normal to the path line. So if you're in a car and you're driving around in circles in the car, you're going to feel an acceleration even if the velocity stays the same. If you're still going 30 miles an hour as you drive in a circle, you're pushed to the side of your vehicle because of centripetal acceleration. But then if you're speeding up or slowing down in a car, that extra acceleration that you feel, that's the tangential acceleration. And the total acceleration depends on change of velocity with respect to position and time. And so you can have both of these accelerations simultaneously. If you're in a car and you're speeding up as you're also going in a curve, you're experiencing both the centripetal and tangential acceleration at the same time. So if we go back to our discussion of steady versus unsteady flow, local acceleration is what causes unsteady flow. It's when the velocity is changing with respect to time. And so du dt is what we call local acceleration. And so the velocity increases over time. That's local acceleration. Now, on the other hand, the type of acceleration that occurs when flow is non-uniform, if the velocity is changing with respect to position, remember we said that if we had some sort of a nozzle and the velocity of the water coming in is 10 meters per second because we've got a big diameter pipe at the opening, if that pipe diameter is decreasing, the water is being forced to speed up because it's got a smaller diameter to flow through because the nozzle is converging. And so as the nozzle converges, that forces the fluid to accelerate. And you can see the exit in this illustration of 20 meters per second means that in the direction of flow, there's been a change in velocity. Anytime there's a change in velocity, there's been an acceleration to cause it. But the kind of acceleration that got caused here has nothing to do with a change in conditions over time, because this is in steady state. It comes in at 10 meters per second, goes out at 20, and it stays that way. Now, 5 minutes from now, an hour from now, conditions are steady, but they're non-uniform. So non-uniform flow, remember, is when the velocity accelerates, the velocity changes with respect to position. So if I'm filling in this table again of classifying flow according to different things, non-uniform flow is caused by convective acceleration. Unsteady flow is caused by local acceleration. So here's an example, and it's one of the few times in the classes that I teach that we'll actually dust off our calculus skills a little bit. Oh yeah, here we go. Don't want to lose this. We've got a nozzle and an equation that describes the velocity inside the nozzle as a function of position. We know it starts off at 10 and then exits at 20, but what is the velocity inside this nozzle that is L long? That L is referring to how long the nozzle is. This formula says that the velocity at any point inside of the nozzle is a function of the initial velocity, which in this example is 10 meters per second. And then by the time it reaches the exit, when we're measuring x from the starting towards the outlet of the nozzle, let me draw what we're measuring x. here is our x direction. Okay, at some point inside here, we can find out what is the velocity here. You know, what is the velocity? We can't just say it's 15, you know, because it may not be a linear change in velocity. It may be that the velocity is increasing really fast at first and then it increases more slowly in the direction of flow. But this equation tells us the velocity at any point in the flow field as a function of where we are, x, relative to the entire length of the nozzle, L. Okay, so we're going to go through and calculate the acceleration, evaluate at the position of interest in order to find the acceleration at a certain location. So if we have L is 0.5 meters long and we want to know at the middle at 0.25 meters, so here is 0.25 meters. Then what is the acceleration at this point is what the example is asking. And to find the acceleration there, we have to find the velocity at that point, and then du dx, which is the change in velocity with respect to position. So velocity times du dx, and the units of that, as we'll see, work out to the same units that you are acquainted with local acceleration. You know, acceleration has units of meters per second squared, regardless of whether it's local acceleration or convective acceleration. Both have these same units. So let's prove it to ourselves with this example here. We've got L of 0.50 meters. An initial velocity is 10 meters per second. And then x is 0.25 meters. Now we've got this equation of the velocity is the initial velocity 1 minus 0.5x divided by L. And we also know that convective acceleration is, by definition, the velocity at a certain point multiplied by du dx. And this is convective acceleration. Du dx is something that we have to evaluate, and to find du dx we're going to use the chain rule, and the chain rule tells us that du dx is du dm times dm dx. And so for the equation that we've been given of u is equal to u naught 1 minus 0.5 x divided by L, we're going to let m, as we're calling it, be equal to 1 minus 0.5 x divided by L. So we're creating some new variable m so that we can find the derivative of m with respect to x. Okay, the chain rule says that u, in other words, u is going to be u naught divided by m. In other words, that can be expressed as u naught multiplied by m to the negative 1 power. If you look at what we have here, u naught divided by all of this is called m now. So we've got u naught times m to the minus 1 power. So what is du dm? Well, that would be d of u naught m to the minus 1 divided by dm. jumped ahead. dx. du dx is dm times 1 minus 0.5x divided by L divided by dx. Okay. So du dx is going to be this new variable m that we're substituting in any place we've got 1 minus 0.5x divided by L. And then we also need to have from over here dm, or so we substitute that in again, what we're saying let m equal relative to dx. Okay, so that is equal to negative 1 u naught m to the minus 1, because it was to the negative 1 power, negative 2 power. And then the derivative of this with respect to x gives us just negative 0.5 divided by L. Okay, if we multiply those two quantities together, it is 0.5 times u naught divided by L, 1 minus 0.5x divided by L, and all of that squared. So we've substituted back in the definition of m. So here we're putting back in this expression of 1 minus 0.5x divided by L, since that was to the negative 2 power. And then we multiplied it by this negative 0.5 divided by L. So it's all in there now. Now we have to evaluate it at our location of interest. We want to know at x equals 0.25 meters and for L is equal to 0.50 meters. Then we're going to substitute in the values. Then du dx, u times du dx, multiplying by the velocity, it's going to be 0.5 times u naught squared divided by 0.5, 1 minus 0.5, 0.25, 0.5, and that is cubed. So if we take the 0.75 to the third power, that gives us 2.370 u naught squared. So for this location that we're interested in at half the distance into the nozzle, where x is equal to 0.25, then the convective acceleration du dx times u is going to be 2.370 10 meters per second squared. That is 237 meters per second squared. So that is the convective acceleration. That is how quickly the velocity is increasing at the certain location that we're interested in. So you'll have a homework problem where you need to know the acceleration as a function of position. And the key there, you may not have to use the chain rule in that homework problem, but the key there is that you have to know the velocity at the location and also the du dx, the rate of change of velocity as a function of position. Multiply the two together, and that's the definition of convective acceleration. Okay, well, that is it for today. I'll see you on Tuesday. Hope you have a great weekend.